Okay, welcome back. So, the thing about Boltzmann's calculation, S equals K log W, is that it gives us an easier way of calculating the change in entropy, which we need to do because if we're going to look at a process, we need to look at the before and the after, okay, so the change in entropy. And for example, let's go back to our particle in a box, or particles in boxes, right? S equals K log W, so delta S equals K log of the final W minus K log of the initial W, okay? The change in the number of possibilities. Thanks to the magic of log, that's K log of the final over the initial. So for example, what's the difference if we add 3 particles if we start with 2? So we go from 2 particles to 5 particles, right? That's K times log of 252 divided by 45. Okay? Because with 5 particles, there are 252 possible ways of arranging the system. With 2 particles, there are 405 possible ways of arranging the system. Okay, so delta S is K log of 5.6, or just 1.72 K. Okay? In other words, we're talking about a positive change in entropy. Okay? Delta S is greater than 0. And in a way, that is what we want to focus on for right now. Okay? Whether the change in entropy is positive or negative. Okay? So let's look at some general guidelines, right? General guidelines for how entropy changes work. So the thing to remember is that going from less free to more free, okay, if whatever system you're looking at is more free when you're done than when you started, then you're looking at a positive change in entropy. If it is becoming less free, okay, if it ends up less able to change with fewer options, then you're looking at a negative change in entropy. So let's just start off with the states of matter, solid, liquid, and gas. Down here at the bottom, you have the solid. Okay, that's just solids are very, very low in entropy. Okay, not a lot of freedom. Okay, all the particles of your solid are locked in place. Okay, they can't move, they can't swap positions. They're usually, not always, but usually in a sort of crystalline arrangement. Crystals have a lot of order in them. They have a pattern, remember? So very low entropy for a solid. And you heat it up, you melt it, you turn it into a liquid. Suddenly, the particles are able to move around. So liquids are more free than solids. They have a higher entropy, okay? So more entropy, more freedom. Okay? Liquids, they can rearrange themselves, okay? They don't have that internal structure in the way that solids do. And now gas, let's go ahead and put an axis over here. Okay, so we're talking about increasing entropy. So higher on the screen means higher entropy. So gases, okay, you heat something up, you boil it. Gases are way more free than liquids, okay? I mean, liquids, the particles are still touching each other, okay, but they're free to move. But gases, the particles aren't touching each other at all. The distances between them are enormous, okay? They're zipping around at hundreds of meters per second. Okay, when you've turned something into a gas, it is incredibly free. Entropy just goes through the roof. Okay? So there's your first good rule of thumb. Okay, going from solid to liquid to gas, you are going from low to slightly less low to really high entropy. Okay? Solid, liquid, gas, increasing entropy. Now, is there a rule of thumb for reactions? Okay, can you figure out, just by looking at it, is a chemical reaction going from reactants to products, is that going to be an increase or decrease in entropy? Is there a way that you can sort of judge that? I wouldn't be asking if I wasn't going to give you an answer. And the answer is yes. Yes, you can. But first, let's go ahead and let's fix this picture over here on the left. It's not exactly honest. Okay, so bing, now it's fixed. Okay, does that clear things up? No, you can't really read it. Well, if you look down here with a magnifying glass, you'll see here's your liquid and your solid, down here bottom left. And way up here is your gas. Okay, I don't know if you can see it on your screen right now, but what I'm trying to do is emphasize that the difference between liquid and solid is minuscule compared to the difference between liquid and gas. Okay, gases are enormously higher in entropy than liquids are. Okay? So when you look at a chemical reaction, what you need to do is you focus on the gases. Okay? The gases are going to be your guide to just guesstimating the change in entropy. Okay? So if there's an increase in gas going from reactants to product, then there's an increase in entropy. Okay? If there's a decrease in gas, then there's a decrease in entropy. So all you have to do is count the number of moles of gas in the reactant side and the number of moles of gas on the product side and compare them. Whichever number is bigger, that's the side with more entropy. Okay? So let's go ahead and take a look at a couple of examples. And our first example for a chemical reaction is the dissolution or the dissociation, the breakup, the decomposition, that's the word I'm looking for, the decomposition of calcium carbonate. Okay? CaCO3 goes from a solid to calcium oxide, which is a solid, and carbon dioxide, which is a gas. Right? So when you go ahead and count these up, you see we have 0 moles of gas on the left, calcium carbonate's a solid, and we have 1 mole of gas on the right. Okay? Calcium oxide is a solid, but CO2, carbon dioxide, is a gas. Okay? So on the reactants we have 0, on the products we have 1. That's an increase in the number of moles of gas, and that means that we're looking at an increase of entropy for this reaction. Okay? Increase of entropy. Our next example, let's look at the combustion of octane, C8H18. That's gasoline. Well, most of gasoline. All right, so 2 octane molecules, liquid, plus 25 oxygen molecules, that's a gas, go to form 16 carbon dioxide molecules, that's another gas, and 18 water molecules, another gas. Okay? Combustion usually involves a lot of heat being released as well, so it's gaseous water, not liquid water. Okay? So go ahead and pause it for a second and do the math for yourself. You back? All right. So when we look at this, we have 25 molecules of oxygen on the left, and we have 16 plus 18 is 34 molecules of gas on the right. 16 carbon dioxide and 18 water is 34 total molecules of gas. Okay? So once again, entropy is increasing for this reaction. So when you're looking at chemical reactions, count up all the moles of molecules or what have you of gas on the reactant side, all the moles of gas on the product side, and compare them. Okay? That's all you have to do. Now I want to stress, this is just a rule of thumb. Okay, this is a rough and ready guide. This is not going to tell you precisely how much the entropy change is going to be, and there are weird cases. Okay? It's possible to have a liquid that is lower in entropy than a solid. It's possible that you can have you can have really weird things. But it is going to generally be the case that increasing freedom means increasing entropy. And increasing freedom largely boils down to the ability to move. If you can move around, then you're looking at higher entropy. And the more you can move, the higher your entropy is going to be. But this does not give you the numbers. Okay? There is a way to calculate the entropy for different processes, and we are going to be looking at that with some examples later on in this lecture series. But for now, just a rule of thumb, more or less entropy. But what does this have to do with spontaneity, I can hear you asking? Well, I'll tell you. Molecules are total hippies. Things like, they want to be free, man. Okay? Increasing entropy tends to mean spontaneous. Okay? If it's not always the case that an increase in entropy means that a reaction is spontaneous, though, but it tends to mean spontaneous. Just as exothermic tends to mean spontaneous, but not always. You can have spontaneous endothermic reactions, and you can have a spontaneous reaction that decreases the entropy of your system. So that is your general guideline for the moment. Don't worry, we will be getting into numbers and math. I'm sure you are pleased to hear that. For those who don't recognize her, over here on the right, we have Janis Joplin, who sang the song, "Freedom's just another word for nothing left to lose." That's just me being a nerd. So now we get into the real heart of the matter with the laws of thermodynamics. You'll just have to sort of take it as a given. The laws of thermodynamics are things that they built up over the course of about a century there, going, well, maybe 80 years. But just by observation, and they slowly built these up. The entropy of the universe will always increase for a spontaneous process. Okay, that's the second law. Okay? So if you were to put it into mathematical terms, it looks like this. Delta S for the universe is greater than 0. Okay? That is the governing principle for whether or not a process is spontaneous. The entropy of the universe is 0. Okay? And this is always going to be true. If anything that happens, the entropy of the universe is increasing. That's just it, full stop. That's why we have a future and a past, and not just this sort of weird muddle. It's because the universe started at a very, very low entropy, and entropy has been increasing ever since. That's what time really is. Okay. Now, just go ahead and remember, going back, way back, to when we first talked about thermodynamics, first semester. The universe is the system plus the surroundings. Okay, so the system is whatever we're looking at. The surroundings are literally everything else. So the change in entropy of the universe is the change in entropy of the system plus the change in entropy of the surroundings. And for any spontaneous process, those two things added together will be greater than 0. Okay. So let's go ahead and look at a couple of examples to see if we can't get a feel for how this works. Okay, so I can get through this first example pretty quick, I think. We have a hot object in a cold universe. What's going to happen? Well, it's going to cool down. But why? Okay, so here we have our hot object in the cold surroundings. Okay, and it's losing heat, Q, to the surroundings. Well, remember, going way back, that delta S is Q over T, right? The heat of the process divided by the temperature at that process, at which the process takes place. Okay? So delta S of the system is negative Q over the temperature of the system. I went ahead and I put the negative sign there just to emphasize it, to make sure it's right there. The system is losing heat. Okay, so delta S for the system is a negative number. The system is losing entropy because it's cooling down. Okay. All right, now delta S of the surroundings is positive Q over the temperature of the surroundings. Okay. Equal and opposite. All the heat that's lost by the system is going into the surroundings, so that's a positive number. And that's what I'm trying to emphasize there. And this is happening at different temperatures because the temperature of the system is different from the temperature of the surroundings. Okay, that's why the object is losing heat. It's because the temperatures are different. And the temperature of the surroundings is less than the temperature of the system. And if you go ahead and remember your math, when you divide by a smaller number, the answer is bigger. Okay? 4 divided by 2 is bigger than 4 divided by 3. Okay? So Q divided by the larger number of the temperature of the system is going to be smaller. Okay, so the change in entropy of the system, oh dear, this is backwards. Well, I can fix it. Boom, it's fixed. So delta S of the system is less than the delta S of the surroundings. And just in terms of absolute size. Okay. It's a negative number and a positive number, and the entropy lost by the system is less than the entropy gained by the surroundings. Okay, so the surroundings increase in entropy more than the surroundings. The surroundings increase in entropy more than the system decreases in entropy. Okay, so the entropy of the universe is increasing. Delta S of the universe is greater than 0. Okay. because delta S of the universe is the entropy change of the system plus the entropy change of the surroundings. Okay? All right. Okay. So that's just directly out of the second law, right? Just based on the definition of entropy itself, the mathematical definition of entropy. The entropy of the universe increases when you have a hot object cooling down. Okay? And that's why hot objects always cool down. If you tried to reverse it, well, that's why things don't spontaneously heat up just out of nowhere. Right? Because the delta S of the system would be less than the delta S of the surroundings. So the surroundings would lose more entropy than the system would gain. So that's why things don't just randomly get hotter. And if they're at the same temperature, the same sort of rule applies. Okay? So there's just no entropy gain for things to randomly get hotter. Instead, everything is going to the same final temperature. All right, and we're out of time for this lecture. We will continue with our next set of examples in the next lecture.